I'm going to talk about the future of JavaScript. I'm always talking about the future. As Santayana said, if you don't study history, you're condemned to repeat it. I think that's true if you do study history, too. So the future of JavaScript is Java. Because that's also the past. I'm only slightly kidding. I have to go back to 1995, which was when I was small, and JavaScript was created in a mad, tearing hurry. And I was thinking about this not only because of Andreas's talk about J2ME.js, but also because, I don't know, I missed the 90s. Vox.com had this picture in their piece about how that was the last great television season, 94, 95. There's like My So-Called Life and Party of Five and Friends. That's when I got my big break. This is me before my hair went gray. JavaScript had something to do with that. I'd go to, back then you couldn't find things on the web like you can now. Now I think you can find a lot of computer science papers, not all of them. Some of them are still locked up behind paywalls. But back then you had to go to a real library and actually read bound journals. And that's what I did. I would go to this place. This is Margaret Jacks Hall, at least the front corner of it, in Stanford University in California. And I would go read papers among the stacks. I also, maybe I went there because I read that John Doerr said, he's a famous venture capitalist, that any idiot could make a lot of money just by hanging around Margaret Jacks Hall. That's the computer science offices. That's where the computer science professors have their offices and office hours. That's where the computer science library is. That's the library that I was going to. I didn't become a successful venture capitalist, unfortunately. But I did read a paper or two, including one about Java bytecode. And this was right before I did the 10 days of work to create the first JavaScript engine. I was still thinking about Java, even though the Java VM that the friend of mine, Kip Hickman at Netscape, had started building had been killed. Netscape was doing a deal with Sun, and Bill Joy at Sun said, we can't have two Java VMs because they wouldn't have bug-for-bug compatibility. Netscape has to use Sun's source code to actually make there be only one implementation of Java, otherwise it'll fail. Now he was right. I think Bill Joy was right. If we tried to reverse engineer or even got source code access and built our own JVM, we would have had lots of bugs getting them to interoperate. And indeed, when JavaScript came out and Microsoft reverse engineered it, there were a lot of bugs in both engines. And we had to write a standard down and work for many years to standardize JavaScript, evolve the standard, build test suites like Test 262. It's really taken a long time. So Java has multiple implementations, but I think all the competitive ones are proprietary. And Java has test suites, but it also has a lot of code behind firewalls, so who knows how well it interoperates. Anyway, I was still looking at Java. There's this paper by Gosling from 95. It's a nice little paper. It talks about Java bytecode. Java bytecode has some issues. Most of the opcodes are typed. Some are overloaded for multiple types, and you have to do crazy analysis to verify the code and do definite assignment analysis and do other things to make sure it's safe. JavaScript was all untyped, so I couldn't use the insight in this paper about modeling the types as you read the code, modeling the stack machine that Java uses in an abstract way, doing abstract interpretation. But I did use that idea for the decompiler that I put in. You know when you make a function turn into a string? In JavaScript engines, ever since I wrote the first one that I'm familiar with, some of them actually go find the source or save the source and give you that source back as the two-string result. The ones I've built up until somebody at Mozilla ripped it out the other year used a decompiler. So they would actually take an internal form like a bytecode and turn it back into a string. And I used the idea from this paper to build that. And I also thought at the time, why do we need typed bytecode? Java already has types in its class files. It has descriptions of all the types of the static and instance fields. It has type signatures for all the methods. Why do we need to have types on the bytecodes too? Here's another thing from the paper. It shows class vector. This is just like old Java. And then it shows the Java bytecodes. And you can see they have names like A-load, I-const, I for integer. A is usually for array. There's no D's here, or B's for Boolean or byte, but it's typed mostly, but not always, which is screwy. When Anders Helsberg was doing the CLR for C# and .NET, all those languages at Microsoft, he fixed some of these problems by making the .NET intermediate representation use untyped bytecode and typed assembly metadata, CLI data. So you could always figure the types out from the fields and the static members and all the signatures on the methods. You didn't need to have the intermediate instructions carry types and proliferate. But there were other problems that CLR bytecode did not fix, or the intermediate code for .NET did not fix. Meanwhile, JavaScript was there, kind of slow in the 90s, but still going somewhere, and finally taking off in the last 11 years, I'd say. So now it's 2014. A lot of water under the bridge. Java's pretty much dead on the client. Plugins, like Andreas said, are a malware vector, especially, turns out, the Java plugin. I think Brian Krebs, security analyst, said that it was the #1, in its day, it's probably not anymore, #1 vector for malware that people would pay for black hat malware that's bought and sold. ASM.js is a thing. It's a subset of JavaScript. It's like carving nature at the joints, like Plato said. It's finding inside JavaScript, thanks to the bitwise and shift operators that I put in that were in Java and C, and I put them in because they were in C. It's finding the subset that is typed in a way that can be very efficiently compiled to the machine, to the metal. And ES6 is all but done. Jason's talk this morning had a nice chart summarizing it, but here's the more hard to read chart. And if you look at who's winning, it's usually, it's IE now. The technical preview for IE now has the most of ES6 implemented. Good for Microsoft. Followed by Echo.js by somebody I knew at Netscape, Chris Toshak. Followed by Tracer, Eric Arvidsson's compiler that compiles ES60 to JavaScript, ES5. And then Firefox 35 is second after the browser in the front, which is IE. Ouch. So ES6 is kind of the last of the bigs. It was so big and so connected, we didn't want to cut it up into pieces. But after ES6, we're going to do smaller annual releases. I'll talk about this in a few minutes. ES6 did absorb typed arrays. So there's that word typed again. Now these aren't like Java typed, like you have to write down the types, but these are int32 array and float 32 array. These are very important for working with the GPU and with SIMD units, which are also coming up. And then typed objects in ES7 kind of take away the wackiness, the fixed length nature in particular of typed arrays, and allow you to have descriptions, runtime descriptions of all your types of your properties if you want to. So typed objects will allow you to imperatively, through an API, not declaratively, say what the types of properties in an object are, and they can be packed together, they can be flat, they can be extremely efficient. It's kind of a generalization of typed arrays. And so then we also have TypeScript and something that it inspired, according to the Facebook guys, Flow. And Flow looks very, very good because they've done a sophisticated analysis, or set of analyses really, that allow them to capture a lot of the idiomatic JavaScript without just giving up and saying, I can't type this, I'm going to just make it to type any. Everyone's really keen on seeing where these things go. But back to the class example from Java, I've rewritten it in ES6 using typed arrays, using a little bit of ASM.js typecasting. Like Andreas said, if you see that vertical bar 0, that's bitwise or 0, that is a cast to int32. And you probably know the other idioms for doing this. There's triple right shift 0 is cast to uint32, and twiddle twiddle x is a conversion to int. And you can do other things pretty efficiently. You can use plus as a unary operator to make arbitrary value become a double. So ASM.js relies on these typecasts. This isn't exactly pretty, but this will generate in a modern engine that can handle the syntax, like maybe the IE preview one, this will generate as good code as any Java VM would on that old Gosling code. So I say JS VMs are basically taking the dynamic untyped route to the same promised land that Java was promising, which didn't get delivered in the browser by Java. It got delivered by JavaScript. We're almost there. With typed objects and typed arrays, I think we'll be there. As Darth said, the circle is now complete. I guess this makes JavaScript Darth Vader, and James Gosling is Obi-Wan. Anyway, let me talk about standardization, because there's always angst about how long it takes to do a standard, and ES6 is big. I was involved in ES4, which helped get the standards body back in shape through the Harmony peace process that I brokered. But, thank you, standardization is going to go faster now. That's Ian Hickson's signature line. I don't know if it's original to him. Things that are impossible just take longer. We're not going to take years and years anymore. We're doing better. Here's how it looked, though, in 2011. When I spoke at TXJS, I took a picture of the TC39 meeting right before then, and it looked like that. And then there's also some famous artist in Italy did a picture of Croc and me. Croc's Plato, and I'm Aristotle. And I'm like, cool it, quit pointing up. I actually miss Croc. He doesn't come to TC39 anymore. And I looked around at the last meeting, and I didn't see him, and I actually felt sad, even though he gets pretty grumpy. But we need the grumpy idealists. We need the Plato. Well, where would Aristotle be without Plato? So now, even without Croc, it's kind of a loss, we have TC39 doing its work on GitHub. My image is too big. You can actually see almost everything that's happening there. I think all the tests are moving there. I believe the specification is going to move there. It still has to be done in Word, if you can believe it, because of the way ECMA and ISO work. But modulo the Word issue, it's also in HTML as a first-class source for the specification. And people can send pull requests. The meeting notes are kept on GitHub and also available on esdiscuss.org. They're captured originally on, I think it's Alex Sexton's OK So Clap, Etherpad, or somebody's. Anyway, ECMA TC39 is no longer working in smoke-filled rooms or arguing in robes in the Greek marketplace of ideas. We're actually working on GitHub, which is good news. And for ES7 and beyond, we're going to work on an annual cadence where it's like the Chrome and Firefox release process. If proposals don't make it through a multi-stage waterfall, they just don't ship that year. They have to take a later train. So the trains always ship on time. So ES7 should be implemented. Some pieces of it are actually implemented now. Should be implemented next year and finalized. There's always a little bit of dotting the I delay. Finalized in 2016, and as you know, ES6 is going to be finalized middle of next year. So standards are getting better. Now, Jason did such a good job of covering ES6 that I thought I'd just talk about a few ES7 things that you might not have heard about. How many people here use promises in some library there? Good, okay. So you may know that generators, which I think Jason didn't cover, are in ES6, and I'll show them in a minute. But this example from Luke Hoban from Microsoft on the he was on the ECMA committee until last year, shows if you were using promises to chain animations, say you had an array of animations, and you use this nice ES6 for let anim of animations loop to iterate over the values of the animations array. It's like for in, but it's over the values. Then for each animation, you'd have to chain using a promise and using p.then to call that animation, and it's kind of verbose. And then at the end, you'd have to worry about whether there was an exception, which you'd probably ignore, and you'd finally, with a final .then at the bottom, return the return value of the last promise, the fulfillment value of the last promise, which is what's being captured by this ret variable. Notice I've used let everywhere, there's no vars. So that's okay, but you can do better with generators. So in ES6, function star makes a generator, sort of like Python, inspired by Python, with some simplifications. And the task.js library from Dave Herman has a function called spawn. You pass a generator function star, to a spawn call, and you get a scheduler in the background that will resume that generator for you. And that generator can then yield each animation in turn. Notice that there are no promises here anymore. The promises are hidden inside the spawn machinery in the scheduler that task.js implements. So already this has gotten a lot simpler because it doesn't have promises with their Lambda callbacks. And it can use try-catch directly, whereas the previous slide had to use the promise.catch method and couldn't use try-catch. Notice also the arrow functions here, which make it nice and short. It wouldn't fit on my slide otherwise. But even with arrows, it's a little much. Whereas with task.js and spawn and generators, it gets shorter and you can use real exception handling with try-catch. What we want to do for ES7 is go one step further. And this is, again, I think due to Luke Hoban originally at Microsoft. And I think this is in good consensus in the committee. And that's allow async to be used as a non-reserved conditional keyword, a contextual keyword in front of function, so that you can make this chain animation async function be an async function. And once you say it's an async function up there at the top, then inside it you can say await. And you see the await takes the place of the yield in the previous version. And there's no function star, and there's no spawn call. You don't need to use task.js. The scheduler gets absorbed into the ES7 version of the language. So async functions will not only depromisify a lot of your code, they will remove generators and task.js boilerplate and allow you to write something like this, which I think is pretty important because JavaScript's going to be async in the browser forever, and it should be. Even if we have lots of new ways of composing workers, and we might end up making ways to make the non-foreground UI thread workers block, async's the way to go. So, and that's true in Node too. So I wanted to share that, and then quickly run through other things that are on board that you may know about. SIMD, I'll give a little demo, is single instruction, multiple data. It's architecture acronym that describes vector units, short units that, vectors that contain integers or floating point numbers packed, usually 4 32-bit floats or 4 32-bit ints, but they come in different sizes, 8 16-bit, 16 8-bit. Generally, they're multiplying to 128 bits. Intel's more recent work also has 256-bit long vectors. And they all get pieced up into power of 2 sizes for integers and floating points. Pretty important for speeding up DSP code, game code, physics code, graphics code. Typed objects I mentioned, value objects, which include, notably, finally, int64 and uint64 for real. And that means we don't want to just hard code these, so we're going to make user-defined operators and literals in the language so you can have your own operators. Probably makes sense for people using matrices and vectors. Even mutable objects could have operators, and you can go to town. And async generators, I showed you async functions. Async generators would be sort of what they sound like. That's something that's being worked on by Jafar Sen of Netflix. So ES7 is going to be smaller, you can tell. This isn't nearly as big as that giant Kangax chart. And maybe some stuff will get cut, but we'll get it done. It'll be spec next year, implemented next year, and finalized into the beginning of the following year. And that's exciting, but nothing beats excitement like a demo. So I'm going to try to show some things here. First of all, this is a demo from the Intel folks showing how SIMD can speed up your code. Here's a Mandelbrot generator. And if you don't have SIMD it starts off a little under 30 frames a second, and it degrades because the complexity is growing as we zoom in. If I say use SIMD, it zooms up by almost a factor of 4. And it will again fluctuate depending on the complexity, but it's still roughly between 3 and 4 times faster because it's getting that 4-fold speed up for the parallelizable parts of the code by using 4 float 32s or 4 int 32s at a time. It's using vectors. So all the additions or all the multiplications happen at once. So game developers and people writing all sorts of things will benefit from this. Now, I don't want to make it sound like it's all about games, but it's important to give games their due because they stress test everything. I think I saw the CTO of Valve many years ago at Game Developer Conference say that only games were really pushing as applications, as a class of applications, only games were really pushing on concurrency, parallel hardware, vector units, SIMD, GPU programming, aggressive memory management. So games are like the really hard case. And this demo I'll start with is the Banana Bread game based on the open source Cube 2 engine, a C++ code base that's compiled to JavaScript by Emscripten. It's compiled to ASM.js. This version is fun because it embeds Doom, the free version. And so you can be in the outer game. I'm going to have to kill this bot before it kills me. There's a bot that's going to come out in a minute. And you can see this inner game is on the wall there. And if you, OK, remove bot. If you hit vertical bar, now I'm playing the inner game. To prove this isn't a video on YouTube, as somebody accused me of running, I'll let you guys tell me which game, first episode, second episode, third episode. You should clap. Third. All right. This one I'm going to use Please Don't Kill Me. I believe control shoots, yes. The arrow keys turn. So the outer game is like WASD to move around. And the inner game is arrow keys. I think I can strafe. Yeah, I can strafe with greater than and less than. And slash does something. I'm not sure what. And there are monsters in the inner game. This is like, oh yeah, do I have to like, how do I hit that? There. Now I'm in trouble. So I'm playing the inner game. The Caco demon. All right. Come on, die. Ow. OK. Now what's really cool about this is there's a, where is it? Oh, it's in my off-screen, Banana Bread. Thank you. Let's get out of this. There's just a few hundred lines of JavaScript to glue the inner game to the outer game using a worker. This is from Alon Zakai. You can see he sets up a worker that contains boon.js. Boon is the name of the free Doom code. And that's in a separate JS file, and it runs as the worker source. And then using sort of a proxy, an ad hoc proxy, he glues the inner game into the outer game. So he sends these messages with names like standard out, standard error, window, canvas along. He can do resizes and renders. He has to clone events, has to worry about mapping the keys through. But this is like a trivial amount of glue code to take two games that weren't written to be embedded one in the other and then put them together. It shows how JavaScript and the web in general are really good for mashing things up, for composition. If you had to write a C++ mashup of these two games, it would be a nightmare. So that's cool. And then this is Unreal Engine 3, which is still a good demo. When I mentioned Java bytecode, here is the new Java bytecode. This is the actual. It's going to take a while. It's big. It's ASM.js, so it looks quite voluminous. But more fun to see the game. Let's go here. So this is, I hope it's going to make sound. I hear it. Does anybody else? I think it's only me. Somebody has to stick a mic here. Oh, good. And then I'll show you my mad skills. These are It's fully playable, smooth, 60 frames a second, and I'm cheating massively. I'm in God mode. It's good. You get really nice effects if you look at the God rays from the sun. See the ray tracing. This is all WebGL and ASM.js working together. This works in, all the browsers are trying to make this work really fast. However they do it, more power to them. All right. Killing spree. Okay, so then I think the last demo I will do, let me see if I can show you the assembly code though. This is the source. There's some handwritten stuff. You see it's very pretty, but then it's prepended. It's concatenated as a source file to the ASM.js code, which is not so pretty, but there's your modern bytecode, right? There's your, Java has a number of if greater than or if equal branching, conditional branching instructions. JavaScript has the if statement. Java has, integer operations. There's your or zero. That's your cast to integer. So I just wanted to show that. Okay, the last thing is not only the Epic Unreal Engine, but also the Unity engine has been cross-compiled with MScript and its runtimes ported to the web. So Unity is supporting HTML5, WebGL as a first-class target, ASM.js as a first-class target. This is Dead Trigger 2. It's pretty fun. The best part of this game is the sentry chickens. They have machine guns on their back. So they take care of those zombies for you, no problem. And again, smooth gameplay. Oh, he's trying to crawl after me. They got him. These kamikaze guys will try to blow you up. So the best thing to do with them is a grenade. I'm not in God mode here, but I'm doing okay. I can take some health just in case. Oh, there's that big kamikaze guy. Watch out. Uh-oh. Grenade. Second grenade. Oh, good. Okay. All right. So, like I said, games are fun and all and kind of violent, but they're also the if you can dodge a wrench, you can dodge a ball test. So if you can run these games, you can run a lot of code. And that's why I always close these talks with this homage to Wesley Snipes in Passenger 57, another 90s movie. It was not that great. Wesley's always awesome when he gets his martial arts face on. But always been on JS. It was never going to win. It was this incredible underdog for too many years. And then when it started coming up, there was still Flash, there was Java plugin, pretty much all JavaScript now. All the browser vendors are acting serious about it. We're evolving it. We're going on to a rapid release process. We're adding all the hardware APIs you need to do everything with the machine. And it's kicking Java's ass. So always bet on JS. Thank you very much.